I'm Anvar Umarov. I'm a software engineer at Yandex Pro, and today we have an agenda that's with a lecture of databases. Then we will have a break with a pizza. There will be pizza time, and after pizza will be a workshop, HR and CV workshop in both the Russian and the English languages. So it will not be a problem to find out the speaker that you want. We have very packed agenda for our lecture. We will try to cover all of these things. It's database types, indexes, transactions, lockings, and architectural problems like replication, sharding, scaling, and security parts of the database. It will be a little bit hard, a lot of information, and that's why we will do some interactions with you. I'll ask some questions. We will have some kind of cases that we need to solve. Okay? Nice. So let's start from the database types. We have this such types: key value, document-oriented, and relational databases. Let's get step by step. For example, key value is the simplest database type. They are very simple. They have only few operations that can be operated. Tautology. They have like put, get, and delete. That's it. You getting your key. You putting your key. You putting a value as a for this key, like here. We have a product 0001, and as a value we have some kind of JSON structure or any structure that you want to put it. It works very fast by the performance because commonly key value databases saves values in the RAM, like Redis or Memcache, and that's why they're getting just information by hash and returning it from the RAM. And they're very scalable because you can host a lot of instances in like many machines, and just the one problem that you need to sync them if you want, or load balance by your service at your own. Okay, next type are document-oriented databases. Who knows a MongoDB? Yeah, nice, a lot of. And MongoDB is a document-oriented database where you have a schema, and in this schema you can save a lot of documents that not requiredly need to be in one structure. You can put in it any documents with any fields, any set of fields. This is the schema flexibility, is a feature of the document-oriented databases. Then you can put in it complex data, like array. Inside of array, you can put a JSON. Inside of JSON, you can put another JSON, and etc., and etc. In relation databases like PostgreSQL, it's a little bit harder to implement it and work with it. And they're also scalable. Commonly, document-oriented databases can work with a large data by the read operations. Okay. Next, and the main part of our today's lecture is relational databases, because they are commonly used in any products, in many products, services, platforms, and etc. It have a structure. You need to write down some kind of structure of your tables, like fields. You designate all of the fields, types. You need to mark down the primary keys, foreign keys, and etc. It uses an SQL as a language. When you're writing some kind of query, when you are writing with a database, you're writing an SQL. For example, in document-oriented databases, you have they have own language for each document-oriented database. Like MongoDB have own syntaxes, Cassandra has his own syntaxes and etc. But in the relational databases, you can simply switch from one database to another. Like in the MariaDB, Postgres, Oracle, they have very similar syntaxes. So newbies will be happy to work with them, work in all of them. And in relation databases, we have such a feature like a normalization. Normalization gives us very good features like system simplification. You don't need to worry about accidental deletions. You don't need to worry about inconsistent dependencies. And what is the normalization? Let's get into it. It has a lot of levels of normalization. There are 5. And the first normalization form says, each cell of the table contains only one value. Table doesn't have duplicate rows, and the order of rows, columns doesn't matter. Okay. In many databases, first normal form is not commonly used. Commonly we use second or third form, and second form, normal form says that all of the from the first form and all attributes that we have in our table, like columns, fields, and etc., need to depend on the primary key. Primary key is some kind of UID or ID that gives you a possibility to mark one row, to divide one row from another as a unique element. Okay. And it looks like this. We have a not normalized table of the orders. We have 1, 2, 3, 4 orders, and we have products as an array and the price of the order. We can normalize it, and we will achieve the structure on the right side, where we have information of an order on the left top side. At the bottom side, we have information of merging orders and products, like which products in some kind of order. Like in first order, we have a first and 2 products. And divided table for just the information of product. So it looks, normalization looks like this. Okay. And another type of the databases is a column-oriented. In column-oriented databases, it very looks like an relational databases, but one key feature is you are operating not with the rows, but you are operating with columns. Why it's functional and where it's used? It's used in analytics, where a lot of operation that we are doing with databases is aggregating some data. Like we want to know in average which each shop making money. We will use an average function, we'll group by the shops, and we'll get this information. And why it faster? Because it saves compress information as each column, because each column have a same type, like an integer or float and etc. And that's why it operating aggregation functions faster, and it's only getting columns that only use it in your query. That gives us also performance in IO-bound operations. IO is input-output readings or writings on the disk. We reviewed database types. Now we're starting to build some kind of project. We have already project, but we want to implement some features and fix some bugs. In our case, is a shop, not little shop. In this shop, we have a lot of products, a lot of orders each day. And these functional requirements that we need to implement. You can read it by yourself. I will read only the functional requirements. About the bugs, we will proceed it further. About functional requirements, we will do a search for orders for shipment, just a little search by some kind of filters. We will search for products by description, like I want to find out how many coffees in my product base, or I want to find out how many products with nuts in it, and etc. And I want to filter them by description, so by text. and the next functional requirement is search for nearby sellers by the location of them, and we will do some kind of comparison seller prices, and a little bit information about SQL and tools that we will use during our lection. We have a very simple structure. We have operators like select, from, join, where, group by. They just words that are understandable by everyone, and it works like we are writing some kind of sentence. Like here we are selecting just columns from flowers. Flowers is a table, and we're joining some other tables by the filter, not a filter, but joining attribute, where we are finding out which column from our original table is linked with the other column from the other table. And also we have where operations, where we are passing here filters, like where flower ID equals 1 and etc. Okay. And the next tool that we will use is a query planner. Query planner gives us two operations. It named explain and explain analyze. Explain only gives you plan of the query that will be executed. So it describes you, I will call these functions, I will call these functions, it will cost you some kind of points of execution. But explain analyze also executes this query actually, and gives you also a time that that taken by execution. And it looks like this. Here we have an explain analyze. Explain gives us a plan where we see like gather operation, and we see parallel scan as also an operation. Operations are marked as a arrow, and we wasted 10 milliseconds to execute this query. Here the scan is a sequential scan of the whole table. And we also have an index scan that works much faster. And we're getting to the indexes. Let's discuss first problem. We need to order search. We need to search on orders. To ship goods, it's necessary to find the list of unpaid orders. Let's mark unpaid orders as a status of pending or another status, but we will work with a pending status. We have 10 million orders. It's a lot for our database. Every day, the number of orders increases by 10,000. It also has a great value. And we have such query. We just selecting. You will see this kind of slides a lot, because for each functional requirement, we will write some kind of SQL. And here we are just selecting order ID, customer ID, total amount, status from orders table, and with a filter like status equals to the pending, and we are just ordering by order date. In a business logic that we are writing, you will have a lot of queries that you will proceed, a lot of business logic that you need to proceed, a lot of HTTP requests that you are doing to the other services, and etc. And if if one of the SQL queries will cost you 350 milliseconds, whole logic will may cost you like 2 or 3 seconds. It's just freezing a moment when you are opening your app and you're just waiting for opening a main page or etc. It's very bad for user experience. That's why we need to optimize it. Let's first understand why it's that slow. We see that it gives you a parallel sequential scan on orders, but in orders we have 10 million rows. That's why it's getting it very slow. And sequential search is doing like just brute force. Is it going of full sequential scan on your table, like 10 million rows, and searching for the pending statuses. How we can optimize it? We are optimizing it with an index. What is an index itself? Index is just another type of data you are imagining, another data type you are imagining. If we will imagine a table by just a table, we will not get the possibility to search faster. And that's why indexes create some kind of other data types, like B-tree or hash tables, and searching by them. So, in this case, we are creating unique index order p key on public order using B-tree, and B-tree will look like this. And this will not deep dive into data structure, but it gives you a possibility to search by the time complexity of log n. That's why we are not wasting a 10 million rows searching, we're just wasting a log n. It will cost you just only few milliseconds to proceed all of the rows. Okay. And we have also another type of index. It calls a hash table. You can create this index also by passing not a B-tree here, but just a hash. It gives you approximately 0.1 constant time of execution. I forget to note that for the activities, we have prizes like a merge for you. Also, you can try your activities at the end at the question stage. But okay. And yes, because of the collisions that you will make the hash bucket feel very badly, you will have also a vector or a list inside of the bucket, and you will need to search out in sequential scan anyway. That's why it's approximately 0.1. Okay, next problem. Not a problem, or feature. How to find an item by description. Does anybody knows how we do it in a Postgres, like just searching for full text search? Yep. Like? Yes. Is it works fast? Yeah, I see the faces that, like, no. Okay. For context, we have 1 million items with their descriptions, and we have 100 RPS that will get into our service for full text search. And we're writing this kind of query where we're just selecting a product, this description from products, and we are searching by description. We are putting like operator that gives you a possibility to search for some kind of regex operations. In this situation, percent signs means that there can be any signs on the left side, and there can be any signs on the right side. So it's just searching for a summer word inside of the description. Okay, and it will work like this. It will go full sequential scan, and inside of full sequential scan, it will go through all of the words that you have in the description. If descriptions are a lot, the search will also be proceeded slowly, and it gives us a time complexity of O n multiplied by k. And let's just try to run, and we have 124 milliseconds. It's not bad, but in the high RPS, it will go slowly and slowly, firstly, and then you have some kind of bad search cases when you need to search for the edge cases. That also will give you bad results as timings. There are two methods of optimizing it. I will show you about this method, 2ts vector, that converting your description to the vector, and you have already implemented functions like 2ts vector and operations of at. You can search it x3 faster. But you also have an index named Jin. Jin does it by on himself. It will cost you more memory on your disk, but it works efficiently. Okay, now we know how to optimize our full text search. Next feature request is to find sellers and products near the house. Does anybody met this kind of problems? Okay, nice. I will tell you a short story when I was implementing trackers for animals, where there was a pastoral project where we are getting little trackers. We are getting on the neck of the animal, and they are just walking. And on the app, you can see the position of these animals, and for the like sheep, cows, and etc. And when they are getting out of some kind of virtual boundaries that you also draw in your application, there will be an alert that that app is sending for you, like your cow is running out of the borders. Let's check him out, and etc. And in this task, I needed this kind of searching for the location types, and we will also look at this kind of indexes. So the same situation: 1 million products, 10,000 sellers, and 10 RPS that getting into our services. In this kind of query, we are selecting seller ID, name, address, and the Henderson formula. What is the Henderson formula? Is anybody knows? Okay, it's just a formula that compares your location with a latitude and longitude, and calculates a distance via some kind of constant values that pass it as attributes of the planet of our planet. Let's check out our sign distance. It's a little bit strange, but we also here have an extension that named gist that can improve your performance over these operations. You just also creating some kind of data structure for these fields, and they are operating your operations on calculating distances much faster. And it looks like this. You don't need to remember all of it. You just can remember that we have an extension like gist that doing this job for you. And we optimized it by 150x by just adding an index. Okay, I think we look at over the indexes and get to the conclusion. Some kind of we have an overhead when we are using an indexes. Why? Because when you create indexes, you need to update them also. Like if you will not have any indexes, you're just creating a table, you're creating, updating, deleting by just one operation. When you're creating additional index, you need to keep in synchronization between these data structures, like in table, B-tree, and etc. etc. And when you are updating some kind of value, you need to update firstly on table, then in the data structures like B-tree. That's why every index will slow your create, update, and delete operations. This creates an overhead. Okay, and selectivity. When you are creating indexes on columns that doesn't have a lot of choices of his implementation for kind of status, or is purchased, like Boolean type, we cannot create just a hash or B-tree index on it. We can create, but if you will have the same count of the truths and falses, it will not work much faster. You're just creating an index for just removing half of the table, but it will last as a big table at all. And fragmentation that we said that with a frequent insert, delete or update operations, we are reducing performance of our operations of the modifications. Okay. Materialized view. What problem we want to solve? We want to find the price range of products for sellers. In our case, it's minimum values and maximum values across all of the sellers. Our query will look like this. We have a select. We have aggregation functions like getting a minimum price and maximum price across all of the, not sellers, sorry, but products. We are operating on the products table. We are joining its prices on the sellers, and we are grouping our product IDs and just getting its minimum and price. Why we need to group here? Because without group, our operations of the min max, they will not work, because it not can get like 10 or 5 or 6 rows that you'll say like min max, min max, min max, min max, and it's just not useful information. That's why we need to group it. And PostgreSQL and other relational databases will throw an error if you will not group them. Let's try to get minimum and maximum price across all of the sellers by the product. We will have 4 seconds of the execution. We don't have a lot of RPS here, but the dashboards will load very slowly. We will have a lot of operations, a lot of other also some kind of aggregation operations. We can create a materialized view that pre-calculates you these values. Like here, it's a minimum value and a maximum value. We are creating a materialized view. We are just creating index for the product ID to just faster find out unique products. And with this kind of materialized view, and we just throwing command to refresh our materialized view, and we're getting 40x performance optimization. We are just get from the 4 seconds to the 100 milliseconds by just creating another view of our table. And we are already not using our minimum and max functions. We are just getting information by table that already prepared for us this information. Okay, good. Materialized view also just a simple part of it. And we are getting to the transactions. And on the transactions, we will review our bugs that we have on our system. And when shipping the goods, it became apparent that more items were sold. Like we have 100 items on our storage, and we sold 105 for some reasons. We have several million products, thousands of orders every day, thousands of sellers, and we're writing this kind of query here. We updating some information. We're setting stock into the minus quantity values, and just checking for the stock is more than quantity to not get into the negative numbers. Not getting negative numbers in our stock field here. And we have normal time for execution. It's okay for us. And we have transactions. Every transaction have this kind of structure, like it have an index ID, begin and end timestamps, pointers, and columns that need to pass it out as values. And we have an error of updating here. When we get a lot of updates on the same time, we can rewrite our stock as a wrong value. When 2 operations will data race and one will update to the stock equals stock minus 5, the second one also will get a stock value. Let's say stock value is 100. One operation get stock minus 11, second operation get a stock minus 15, and they data race it. Both of them get a value of the 100. One set it to the minus 11 and second set it to minus 15, and as a result we have 85. But we needed to get 74. This is a data race. And to solve these kind of situations, we have transactions and lockings. Transactions covered by the principle of ACID. It says that it need to cover atomicity. Atomicity is treated as a single individual unit of work. When you're operating with a lot of operations in SQL queries like select, update, delete, and then etc., and you need to do it in one business logic. For example, on the previous case, we can imagine a business logic that gets from other SQL count that we need to decrease, At the second operation, we are getting count that currently saved in our database, like stock 100. And we are setting a new operation that saves us a stock as 100 minus 11. And it will get you a situation of the data race. That's why we have an atomicity. So atomicity provides you a promise that all of the operations will completed successfully or none are executed at all. Consistency. What consistency says? That before of your transaction and after your transaction, table will stay consistent. It will not break for some kind of foreign keys or primary keys, and etc. Isolation, and each transaction is executed in isolated environment and can get values that like by the time of executing one transaction, the second transaction will not be able to read information from another transaction. So it will give you a solution of the problem of read uncommitted. We'll review also these problems. And durability. Once transaction has completed, it's permanently saved, even if your database will crash or another break will occur. So, what isolation levels we have in the transactions and what kind of errors we can get from it. 4 levels. There are read uncommitted, read committed. This is a problems like repeatable read and serializable. First of all, we have a problem of read uncommitted. Another problem here is two transactions that operating in the same time, as you see. First transaction gets you a balance, it gets you 100, and then he wants to update. But second transaction getting in between these operations and updates it by 100, and in some kind of time we have a value of 200. If we will not have any isolation here, first transaction also will update it to the 100, and if transaction 2 will broke or roll back some kind of way, first transaction will save the value of 300, because we read the 200 on the stage that we are getting an update on the first transaction. Next level of isolation is read committed. Two transactions modify the same data, and we here have the lost update problem. When first transaction begins the operation, second transaction reads some kind of data, first transaction updates the data, and second transaction updates the data, and we getting an inconsistent situation because second one read it not appropriate value and save it not appropriate value and not kind of counted first transactions operations. Okay, and also we have a repeatable read. In this level of transaction, it's impossible to reread modified and written data if that same data was previously read before the changes were made. What it says that you can start this kind of level transaction on PostgreSQL with begin transaction isolation level repeatable read. When you starting read some kind of data, the second transaction will not be able to read it also, and will wait for the ending of the read operation and all of the operation done, and the second transaction will update this value, and the first transaction will not be able to read it and will return some kind of other value to the get operations. It's the same situation as our friend said, and it's like it's okay error for once in a while for the users to get a little bit wrong value for a couple of times. And we have last isolation level is a serializable. It will block at all of the operation between transactions. It will say that all of the transactions will executed sequentially, and we have no errors here at all, but we have terrible performance here. because all of the transactions will not can get operate parallelly. Okay. We get this information. We have 4 isolation levels. All of the isolation levels have some kind of errors, but you need to use them correctly on each situation when you have some kind of operations with the money, with another kind of strong double checking values like money and etc. But you also need to work about your performance. That's why not need to always select the serializable as the only option. Okay, for example, we implemented our isolation levels for our queries, and we get out of the error of counting our products after they. Now we are getting some kind of other errors. We are getting like just exceptions, just troubles that our Postgres throwing at us, and we need to fix it. But how? Let's get into it. It's about lockings and deadlocks. Now we're getting to the lockings. We have several types of lockings, like table locking, read locking, and I wrote it wrong. Row locking, not a row, like row. Okay. And we have 2 types of the lockings itself. It's shared locks and exclusive locks. With the shared locks, shared lock can be applied to one row or several rows, but many transactions can apply to the one row many shared locks. They can read it, but there will not be possibility of updating it before all of the read operations will execute it. And we have also an exclusive locks that can be applied only once at a row by with one transaction. It gets rid of all fully of the other operations like read and write. And with the syntaxes, as you see, you can select balance from T account for ID1, for share if you want to apply shared lock, and for update if you want to apply exclusive lock. I do think that we have a deadlock here, that because we are updating balance as a ID1 and waiting for transaction number 2 to apply update on the where ID1. I think we forget here to implement an locks here, but we have a deadlock here, and both of the transactions will get lost by both of the update operations and get stuck, and we will catch some kind of deadlock. And this kind of situation need to be solved by code. You need to review your database operations, and there will not need to be such of kind of operations when you're looking other rows by the 2 simultaneous operations. Okay, and here we have the same query here, but with an exclusive lock here for update, and that's it. Just an example of how we apply exclusive lock. Just selecting stock from seller stock, and nobody will able to update it or read it before we will select it in the transaction. Generalization is the same operation of normalization, but in reverse. When we were normalizing, we wanted to achieve the normal form when each table have smallest information about other entities. But here we are trying to denormalize it, but for the next problem. We normalize it very well, and now we are not able to get full of the table with a high RPS. And reports during shipment put a heavy load on the database. That's why we are getting slow performance. For example, we have a such table. We need to get a lot of fields from it to generate some kind of report. like orders information, customer information, like phone number, email, location of the order. And we are saving this information in many tables like orders, customers, products. And for each row, we need to also get a description of the product and etc. and generate a big table of the report. And we have this kind of query. We are selecting something. We are joining something. Many tables, like 3 tables here. It will give you 136 milliseconds. And for example, we are opening our main table very oftenly. In this case, also our database will struggle on the performance. These kind of problems will occur in any project. There are a lot of cases where you're getting this problem when your tables on the admin panel are loading very slow. And you can just optimize it with just saving your informations, some kind of few informations to the main table of the order details, like save all of the information to the order details and get all of the information that you need on your admin panel from here. Don't need to add all of the fields that you have on other tables like customers, gender, customers, what have customers have, leg number, or etc. But just saving here information that you needed by an admin panel. And it will give you a lot of performance boost because you are not joining nothing, you are not applying some kind of search on an index of the joining attributes, linked attributes by the foreign key. That's why we're getting very nice performance boost. Okay. Now we know one little trick that will help us further. Let's get into the next stage of our speech. It's about an architecture. And it's about an replication, sharding, scalability, and security. Main reasons of doing a replication that you are struggling with a load that gets as a traffic on your table or in your databases, and you already cannot do some kind of vertical scaling, and you want to make a horizontal scaling with a replication. And you have many read requests. With write operations, there is a replication will not help as much as you think. And also, in the case where there are a lot of users around the world, a replication helps as a CDN. So you're putting around the world your tables as some kind of cloud service. And also, there will need to be a services that parses this request to the correct database. So let's get a situation where we have an application that sends an accrued operations to our relational database. For example, Postgres. It gives you create, read, update, and delete operations. If we will divide them by 2 groups, is a mutation operations and read operations, like read and write. The common way of the replication and the most consistent way is having a master-slave architecture. When you have one master, when you're writing all of the data, and slaves, replicas, where you are reading information. In this kind of architecture, you can grow as much replicas as you want, but the one minus, the one cons that if you will have a lot of replicas, there will be no resources for a master to synchronize them, and you will get not last updated values if you will have a lot of slaves. And this is a structure of the replication. It's very simple, and the master sends some kind of val files that saves all of the information that gets some kind of mutations, sends it to the replicas sync out, and you can get up-to-date information with the read operations on the replicas. But also, there is a possibility to read from a master. You can choose by yourself if you want really maximal up-to-date information you can also read from master. But you cannot write to the replicas because replicas don't do synchronization operations, and you will just lost your information. And advantages of replication is a read scalability. You will increase your traffic on the read without some kind of errors, but you will get a little bit out of sync problem, but in the many cases it's not terrible. You can get a geo distribution of your request, as I said. You can buy many machines on your cloud services, and make also in the services itself. Your backend need to be there. And fault tolerance, as said our friend, that if some kind of machine will drop off, break or crash, etc., or your hosting say that they are not working anyway for a whole day, you will be saved with this kind of operations. Okay, and the sharding. It's a brother of our application, but it needs to be operated by a large amount of data. When you need to divide your data to the other segments that you can operate, this also removes traffic by write also. You can shard it by a lot of masters, as here, and your write operations also will be sharded by some kind of hash or etc. And I know a case when some social network applied sharding on popular actors and actresses because a lot of traffic was generated by a single persons. That's why there was a need for shards that will segregate some kind of not popular people with one or few popular people, so the request will be proceeded faster. And yes, replication can be friend with the sharding. You just sharding, then in each your shard you're just replicating it, so you will have several masters as a count of you have of shards. Okay, and advantages, scalability. We want to grow up our traffic. Our traffic is growing up, that's why we need to proceed more traffic. Even node load, so you're dividing load by the nodes. It will work much better for than replication if you have the same operations of the read and write, and even each node will have same load as a CPU usage or the RAM usage. And even data distribution also helps not to grow up your disk size. Your disk size can be also smaller, but you're just getting solution via horizontal scaling. Okay, and about fault tolerance. What is the tactic that we are applying when our replica is crashing? All of the read operations, as you see with a bolded arrow, all of the read operations goes to the master, can go to the master if you have only one replica. You can have two replicas. If you will have two replicas, if one will fall, all of the operations will go to the second replica, but be sure that every replica can take a load of x2 of the one replica. Why? Because if your one replica are getting 80% CPU usage, 80% of RAM usage, and all of the requests in the same time will go to the one replica because one of the replicas was shut down, you will get x2 traffic, and a second replica also will shut down. That's why we need to keep in mind that we need to also vertical scale our replicas. In case we will have that master will shut down, any other replica can become a master because it's partly synced with a master. And after shutdown of the master, the best solution is to make some kind of replica to become a master. We will lost some data, but after our resolution of our master, this data can become restored, but in many cases no, because you are already proceeding update, delete, and create operations. You're losing some bit information, but you keep working, but your product keep working. Okay, and fault tolerance. We have a data replication. Replication can be synchronous when all copies are updated synchronously, or synchronous when copies are updated as the resources allow. And always backup your information, because if all of your masters will break down or anybody will delete your information, you will have backups, so you can restore all of the information, or you can simply delete all information without some kind of WHERE filters. And sharding is also, it keeps your fault tolerance, because in case of failure, you just losing some part of the information. And if you have some kind of smart synchronization between nodes, so you're trying to save 2 copies on the 2 or 3 shards, you will not lose data at all if you will have a shutdown on 1 shard. And of course, vertical scaling. We can throw money on our servers. They become bigger with a CPU, with a RAM, with a disk, and we are happy in the short term. Some kind of high demand times, you can apply these tactics. It's not strange. And security, there's a bit tips about security that also can be applied to our databases. In Yandex, we don't have privileges to write, update, delete any data from the production databases. And in some cases, we even don't have read operation on databases, because there can be personal data. That's why developers there is no need to have access to the personal data of our users. That's why you need to keep less privileges on your developers if you are designing your databases. You need to sanitize your input, so there will not be any SQL injections. By sanitizing, I mean just not to write SQL queries like with a concatenation of your WHERE filters. There is a possible ways to pass an argument to an SQL query, and Postgres will handle it by yourself. Data encryption, of course, data encryption need to be applied between your service and the database. If you passing some kind of other servers to get into your server. If you have some kind of internal network, there is a way that you don't need to have data encryption, because it's an internal network. But in this case also, there is a mistake that can be making if hackers will get into your machine. They can read information between these HTTP requests. Backup, as I said already. And audit and monitoring. By audit and monitoring, which part of the database monitoring you can say what we need to monitor about our database?
Yes, so you were mentioning that, for example, the replicas and just the database in general, they should be able to handle the load of like X2. So like in monitoring, maybe we could see if we have enough resources.
Nice.
For example, like as the users amount grow, the number of queries grow, and we could see that, okay, we need to allocate more resources here or there.
Yeah, perfect. If I will translate, we need to keep eyes on the CPU, RAM. We are talking about monitoring exactly on the database side. That's why we can keep an eye on CPU usage, RAM usage, disk usage, network usage also helps here. And as we said, there will be very helpful that we see how many how much time our query is executing, and also one very functional thing that in every query, when you're executing them, they are executing on some kind of stage. For example, by CPU usage, by the RAM usage, by the weighting, CPU weight, RAM weight, or disk weight, and this information also can be get out of our database, and we can see each query how many time wasting on the disk weighting or the CPU weighting, and it's also very helpful in debugging of our queries. We don't need to run a lot of explain analyze operations. We can see that our operation is wasting a lot of disk, so that we can apply materialized view, because it already keep in some kind of state our aggregations. Okay, I think that's it on our side. There will be conclusions that we are learned a lot of things like database types. We have a very pretty, how can I say, painting where all of the databases are. I forgot in English. There is every database in a with some kind of commentaries like key value, data sets, and etc. And we learned about indexes, we learned about transactions, lockings, about scalability. Thanks. Okay.